discuss the maximum variance perspective. Essentially, we will view the problem of principal component analysis as a problem related to filling space. In this figure, we give an example of how two-dimensional data can be represented by a single coordinate. In the right panel, if we choose to ignore the x2 coordinate of the data because it does not have much information, then we can view this as one-dimensional data. We could have chosen to ignore the x1 coordinate, but then the compressed data will be very dissimilar to the original data, and the information in the data would have been lost. If we interpret information content in the data as how space-filling the data set is, then we can describe the information contained in the data by looking at the spread of the data. We know that the variance is an indicator of the spread of the data, and we can derive principal component analysis as a dimensionality reduction algorithm that maximizes the variance in the low-dimensional representation of the data to retain as much information as possible. You can see that here in the diagram. Considering the setting that we discussed in the previous section, our aim is to find a matrix B that retains as much information as possible when compressing data by projecting it onto the subspace spanned by the columns B1 through Bm. Retaining most information after data compression is equivalent to capturing the largest amount of variance in low-dimensional code. That's a result of hoteling. The data covariance matrix S equals 1 over n times the sum of xn transpose. We assume centered data. We can make this assumption without loss of generality. Let's assume that mu is the mean of the data. Using properties of variance, we obtain the variance of z equals the variance of B transpose x minus mu, which in turn is equal to the variance of B transpose x minus B transpose mu, which is the variance of B transpose. That is, the variance of the low-dimensional code does not depend on the mean of the data. Therefore, we can assume without loss of generality that the data has mean 0 for the rest of the section. With this assumption, the mean then of the low-dimensional code is also 0, since the expected value of z is equal to the expected value of B transpose x, which is B transpose times the expected value of x, which we just assumed was 0. In the next video, we'll set up the principal component analysis problem as a constrained optimization problem.